So good afternoon everyone. Today we will discuss this topic, implementation of optimal receivers for Awgn channels, right. So first of all, the optimum receiver, the definition of optimum receiver, why, and then why we are going to discuss it for Awgn channels. As we discussed earlier that Awgn is additive white Gaussian noise, and while we are discussing this type of channel, we are isolating it from all other sources of noise, right. And secondary, because in the deep space communication, this is mostly unexplored or explored earlier also. So we'll be targeting it in for both the purposes. In optimum, we'll go for like maximizing our correctness of decision. What is the probability of our correct decision? We are going to maximize that, and what is the probability of our wrong decision? We are going to minimize that. So error will be going to minimize, and the correctness will going to maximize. So here we will discuss first, which is the correlator method. In that case, we will see its structure and how we are going to perform that with the help of different equations and its structure. So we will go for that, but before that, as we know that any signal which we are going to transmit is SM. This is basically we are going to transmit from 1 to 3 M up to capital M. So this is our signal which we are going to transmit, and in this case what will happen, this is say S1, S2 like that. So these are all statistically independent. This is the first thing. Second thing is, while we feed the signal to the channel, so this is channel, or we can say this is Awgn, which is a source of noise. Then we receive R. So you can say this is RT and NT, right. So in this case, this is noise and this is our received signal. Now on the basis of our received signal, we are always going to take a decision that how we'll decide that whether S1 was transmitted or S2 was transmitted. Basically, we'll create one vector space at the receiver end, and for the decision boundaries, that will be saying we are having a vector R and we are having different components under this, and depending upon our observation vector which falls in a particular area. Now depending upon that decision area, we'll be deciding whether we have transmitted S1 or S2. So to know that, we must know few things, that what is the probability of transmission of a message, that is probability of, or we can say PM, this probability of the message which we are going to transmit, say P1, P2, P3 or P4. So in that case, what is the probability that S1 will be transmitted? Say we denote that by P1. What is the probability that S2 is transmitted? That we denote by P2. So as your PM. Now in this case, why this is important? Because there are many situations or the applications where our probabilities will vary. Like we will call, say, the temperature condition or temperature controller of this classroom. You will find, if you are going to send a message outside to the controller, 1 if the temperature is high, and so if the temperature is high, and 0 if the temperature is under control. So you will find that many of the times we are transmitting 0, and very least time we are transmitting 1. It means the probability of transmission out of these two, 0 and 1, will vary. It is not equiprobable. So, but we may have certain conditions where we'll have, there are equal probability, that half probability for transmission of 1 and half probability for transmission of 0. Now if we come to the maximum A-Posteriori rule, then we'll find that we say the message which is detected and the maximum of eta m plus r dot Sm where right. Now, in this case we will see m kappa is, this one is the message our receiver will decide that we have detected this one, and this is from all the variables which we are having, the message m1 to capital M. So, all the messages which we are going to decide, then thereafter this is the biasing factor we will say, and its value is dependent on noise spectral density and not, and the probability, log natural log probability of the message, and this is given by the norm. While calculating the norm in the Gram-Schmidt orthogonal procedure, we must have discussed this point, that if you are going to have first condition for orthonormality as the two vectors must be orthogonal, and second is unity norm. So, the norm should be unity norm. So, this is the norm of that message. If you are having message S1, so norm will be eta 1. This for S1 say this is denoted by, and for SM we say we are denoting it for AM, right. So, this is for our what we call as biasing factor. Now, in this case, how to implement this thing? Now, the question is of implementation, how we are going to implement this thing. Now, we are having this R which is a vector, and this SM which is the signal or the message which was transmitted. Now, this vector R, while we will talk about our receiver, will be having input in terms of RT. This receiver, and with the variable say your signal, we call it as RT. Now, we are having RT in the input. Then how we are going to take up the values or the vector as R? This is basically done with the help of our basis functions. Like in case of orthonormal procedure, we must have discussed some of the basis functions, phi 1, phi 2, say phi 3, like that, for one vector, for another vector. It is similar to like we give the directional and magnitude of a vector. So, this is related to, similar to that you can say, and in that case we will multiply if our RT with their projection vectors, then we will have our received vector R and integrate that. So, we will write it in terms like or before that we can say this one. So, this is the receiving, and this is a variable R1, R2 integration, and then these projection vectors. Now, if you are having n types of n numbers of these projection vectors, then we will be writing it for RT, then phi 1, then phi 2 up to phi n, and then we will find, integrate it, and then ultimately we will find our received vector R. And then if our received vector is available, then we can multiply them and we can find out this argument, and by maximizing we can make our receiver to be optimum. Now, we will discuss the structure where we can have this kind of situation, that we are having this RT, R from RT. Say this is our received signal, which we will call as RT. Then we have these basis functions, say phi 1 t, phi 2 t, and here say phi n t. Then we are going to take integration Right. Now, if you look into this, we have received signal RT. Now, from this received signal, if you are going to multiply this with the phi 1 t or the respective projection vectors phi n, then we will have, after integration, we will have the components of our received vector R. And if we will add them up, we will take the information of all, we will find our received vector R. Now, if our vector R is available, then the next step is we are going to multiply it with different message signals that we are going to transmit, S1, S2, S3 up to Sm. Now, in that case, we can write it in that term, this is R, and we will be using this correlator. Now, we will see this is the correlator, these are vector which we have received R, then we are going to multiply it with S1, S2, S3, S4 up to Sm. Now, in this Sm we will be having different outputs R dot S1, R dot S2, likewise R dot Sm, and then there this eta 1, 2, 3 and up to Sm. Now, in this case, in the final, we can say select the largest and will give a output decision, whichever will be maximum, and will say this is similar to your MAP criteria, maximum A posterior criteria, that if our value is maximum out of these, so we will decide that if this value is maximum, then we will say that message S2 was transmitted. So, this is the one way we are going to implement this structure for optimum receiver, and we call this structure as structure of a correlator receiver with an correlators. Now, in this case, you see why we have written them as separate one, because they are dependent on individual probabilities of the message which are to be transmitted. Because if you will see its composition, it is n naught by 2, we can write there, this is say n naught by 2 eta m Pm minus m, right. So, you will find this has to be separate for each of the this correlator branch, and it will be written as eta 1, 2, 3 and all. So, in this case, if you review it again, then you will find that we are going to implement this optimal receiver based on this structure, which is basically a correlator structure. The correlation will be done here, that we are having received vector R. Since we do not have at a receiver this vector R, we will be just having RT, that signal, received signal RT. Now, from this RT we will be multiplying them along the projection vectors, and then by integrating them we will be having their value R vector, and then with the correlation of all the messages, all the possible messages, or we can say if we have selected only 2 messages, then we will have correlation up to 2 only, right. And what is the benefit of having this? Because if you will see, you have transmitted cos 2 pi f c t, and another is minus cos 2 pi f c t. If you multiply together, you will automatically come to know that if it is from the same signal, then that value will be the maximum, otherwise it will be least, because they also follow orthonormality and prior to that orthogonality. So if they are orthogonal, then we will be having only one value which is going to be the largest, all other values will be the minimum, and we will select the largest, we will give this one. Now in this process, there are certain points which we can observe, that some of the values are not dependent on the messages which are to be transmitted. Now can you find out which are those values that which are not dependent on the message or the received signal? If we talk about this value, whatever we are going to receive, it is not going to be a variable. And if you talk about these values, S1, S2 and all these are again not dependent on our received value RT. Whatever signal we are going to receive here as RT is not going to vary our value which are in this term S1 or to SM or with eta 1 to up to eta m, because now eta m is dependent on the values which are PM, probability of the message, and their norm of the message. And similarly, these are the messages which are going to be transmitted, and all these messages are again statistically independent. So now from there, there can be another mechanism that we can club up these things into another correlator receiver that we will discuss after this. But if you implement this optimal, then what will be our output? Let us see that output of detector. And that is m kappa, which is going to be detected maximum m plus RT every and now that is our message which is to be detected, RT, SMT, and in this case you will see we can directly find out this vector R dot SM. Instead of having those projections, if we will receive our signal RT and multiply it with the vectors S1, S2, S3, we can directly have R dot SM, and this modified structure will be similar to. Okay, before we go to that, one thing which is important is that we are having these n types of the basis functions, and m is a number, our messages are there, right? So this structure is helpful while this n is less than m, or in fact it is much less than m. And the next structure where we can find out directly these values is a simplified version of this, and we can note out that, say this is our received signal RT, S1T, S2T, Now see in this case, what modifications we have made compared to the earlier one. Now in earlier case, we are having some projection vectors, and then we are finding out this vector R, and then we are going to find the correlation with the SM. Now in this case, we are doing it directly, multiplying it with the RT, all this. Then we are integrating and then giving our this vector eta 1, eta 2, and then we are maximizing it. And the structure of, and this structure is correlators, correlation receiver with M correlators. I will see in this case the number of correlations required are M, up to this M. In earlier case it was up to N, and N is your projection vectors, so phi 1, phi 2, like that. So in this case we will be having this multipliers, so these correlators are basically the multipliers and the integrator. This combined unit we call as the correlator, this one, first multiplier and then integrator. So in this case there are certain advantages and disadvantages. If we will find out those, we will see in this case we require at least M number of correlators, and in the previous case we required N number of correlators, and we will see if N is less than M, then we prefer the previous one, and for M, N is equal to or greater than M, we prefer this one. So in this case, what is the drawback? Drawback is we require large, our circuitry will be complex at the receiver end while we are going to implement all these receivers, either N number of receivers, correlators, or N number of correlators in both the cases. And this problem can be solved in case we use a match filter. So in the next we will discuss this match filter.